So as I mentioned, the permit essentially establishes an integrated BMP sizing approach where we have 3 overlapping performance standards. The permit doesn't say that you have to achieve each of these separately. In fact, probably you'll see folks trying to combine all 3 of them into a single facility that can achieve LID treatment control and hydromodification control. I will note that LID and treatment control are essentially one and the same. When you've met your LID obligations to retain or biofilter the 85th percentile storm, then that fully complies and checks the box for treatment control. But the inverse is not true. It's the hierarchy that we've been talking about. Yeah.
Just a real quick question on that. Can you go back to the last slide?
Uh-huh.
Those are infiltration BMPs directly adjacent to the structural supports for that overpass?
Yep.
Oh, interesting.
This is important.
Geotech concerns for that?
No, this is in Portland, and this is on pretty nice sandy soil. I've commented on this. I use this as an example of it's not always what it appears. We also have the Willamette River nearby with its normal water level about 30 feet below this ground surface, but with its peak flood elevation maybe 5 feet below this ground surface. And I believe this parking lot's been flooded before in major events. And so I'm not sure how they quite deal with the seasonal high groundwater level issue here, but what I will say is I bet those supports were designed for full saturation of the soil. So you can design a geotechnical structure to be okay under full saturation. Yep. So as I mentioned, three typical scenarios are going to occur. We're either going to have sizing controlled by hydromodification, sizing controlled by LID, or alternative compliance where both LID and hydromodification don't fit within the site entirely. And so we can think about this in sort of relative proportions. Whenever we have HMP criteria in place, we've yet to see a site where HMP criteria would be fully met by the design capture volume. And so you're typically going to be designing with those controlling, whereas in an LID controlled case, it's only going to happen where streams are not susceptible to hydromodification. And so this module, all the sizing calculations I'm going to present in this module, the tables, the figures, and all that are really most applicable in cases where you're not discharging to a susceptible stream and LID is controlling the sizing. So if your jurisdiction has only susceptible streams, you can feel free to take a walk around the block right now. So when we read the permits just said retain the runoff from the 85th percentile 24-hour storm event. And the problem with that is it doesn't specify how long that water has to sit around and what we need to be able to make available for the next storm event. And so in the interest of actually moving the ball forward and making sure that development BMPs actually work, what we added to this as part of the technical guidance document and model WQMP is that if you're using a simple design storm capture method, you need to recover that storage in no greater than 48 hours. And this is what we're referring to as a simple design capture volume method. So you need to provide a simple design storm method for folks who want to do things very simply. But what we also established here is that combination of capture volume and drawdown time resulted in a level of average annual capture. So 100 acre-feet runs off of this parking lot here over a 40-year period. The standard we established was that you need to be capturing and infiltrating or treating 80 acre-feet of that. So average annual capture is not that every storm you capture at an 80% level, it's that on a long-term basis, 80% of the total runoff gets captured and either infiltrated if feasible or treated to the extent that it's not feasible. And so what we've established here are two parallel and equivalent standards. One, which can be demonstrated very simply just by providing a volume and showing that it drains in the right amount of time. The other, which is based on either someone doing a site-specific continuous simulation analysis, like the SOCM model that Daniels and Remy are going to present, or using the nomographs that we generated as part of the document, which can help someone estimate what is required for 80% average annual capture. And so we call this one the capture efficiency method. In addition, what we have added on in South Orange County is that if biofiltration is used, as I mentioned, the pre-filter storage volume in the surface ponding and the pores can't be less than 75% of the remaining DCV, regardless of how you do your drawdown and routing as part of the capture efficiency method. And so these are some nomographs from Appendix 3 of the TGD. And so what you can see is that if you've provided the design capture storm depth 1.0 times the design capture storm depth up to the 48-hour drawdown time, you're right at about 80% capture. So this is the basis for the equivalency that we've established in the documents. But what you can also see is that if someone can't, for example, drain in 48 hours, they still want to size BMPs to try to comply. They can't drain in 48 hours. Say they can drain in 72 hours. Then they can read up what does it take to get to 80% capture. Well, it takes me supersizing my BMP by about 20%. And no, I can't drain in 48 hours, but I've upsized my BMP to accommodate for that, and I've still demonstrated that I can achieve 80% average annual capture. And so that's also compliant. On the flip side, if someone has a BMP that can drain in, for example, 12 hours, for example, a 12-inch BMP at 1 inch per hour design infiltration rate, let's take a look at that line, and read down. And we're at about 0.55 inches, or 0.55 or 55% of the design capture volume that they would actually need to provide in that infiltration BMP. And so I would note that this can be an option that would allow someone to get significantly more efficient about their site design, where their soil conditions allow them to optimize on that. So drawdown time, you're going to see a lot of emphasis on drawdown time in the sizing calculations. This is a pretty simple calculation for a lot of BMPs. Most of the time it's just, what's my equivalent water storage depth? So it's my ponding depth plus whatever my pore depth is here and whatever my pore depth is here, divided by the average discharge rate, or the average infiltration rate, and that's how I calculate my drawdown time. Some types of BMPs, like an infiltration trench that infiltrates out the walls and the bottom, the proponent might provide an alternative method for calculating drawdown time. But drawdown time is really important in all of the sizing calculations. And the reason why it's important, of course, is because a well-behaved BMP that drains in 1 to 2 days can be ready for the next cell of events. Not always, but more often than not, it's available for the next cell of events. Whereas this is a hydrograph for a hypothetical storage and harvest and reuse system in Orange County. And what we see is the timescale of months here, a system that fills up in late January and stays full and bypasses for most of February before it starts to drain eventually. And you can imagine that the majority of the average annual runoff actually bypasses this type of a system. So this is just the text from the permit again to describe what is required for biofiltration BMPs. And so when we talk about this pre-filter storage volume, we think about this volume plus the pore volume here not being less than 75% of the remaining design capture volume. So that comes in essentially as a check at the end of the sizing calculation. Okay, so now that we know what's required, a thought process that we can put forth to folks about how to think about sizing. And one of them is to claim your hydrologic source controls. Yeah, stretching? Okay. First is to claim your hydrologic source controls. And then next is to provide LID BMPs for what remains. And so the basic hydrologic calculations are just a simple runoff coefficient method where we're multiplying the runoff coefficient by the depth of the storm, by the area of the site, and then some conversion factors to convert to cubic feet. And so a typical design storm calculation is going to look like computing the imperviousness of the site, and computing and estimating the design storm depth, going to these calculations, calculating your runoff coefficient based on your imperviousness, calculating the volume based on the runoff coefficient in the drainage area. So these are, we've tried to keep these calculations as really as simple as possible. So one thing that I want to stress is that when we calculated the imperviousness of this project, we didn't go to the hydrology manual and look up multifamily and pick 80% from the chart. And the reason we didn't do that is because that doesn't incentivize a reduction in impervious area. That doesn't help relate the actual decisions people are making about site design to how that influences the BMP. And so what we ask folks to do is, we should be asking folks to delineate the actual impervious area of the site so that if they can reduce that impervious area, they can get credit for it in terms of a lower design capture volume. So what's the role of hydrologic source controls in sizing? We can either identify areas that are self-retaining, that meet the definition to be self-retaining as defined in each one of the fact sheets for the hydrologic source controls. Green roofs, when they're designed in accordance with Appendix 9, are also considered to be self-retaining. But more often than not, we're going to find HSCs being used as basically a way to reduce that design capture storm depth to something less, essentially shave the base off the hydrograph and result in reduction in sizing downstream. And so I'll go ahead and describe an example calculation. So we'll take a look at this. This is a chart from the fact sheets, and in this case, what we have is a total impervious area of 12,750. We have 10,000 square feet of impervious rooftop drain into 5,000 square feet of lawn. So the critical factor here is the ratio here. We have 5,000 square feet of lawn receiving runoff from 10,000 square feet of impervious rooftop. So our ratio is 0.5. So we start with 0.5, we read up on the chart, we read over, and what this has gained for us is a reduction in, an effective hydrologic source control retention depth of 0.25. Now we'll area weight this with the rest of the chart. We say we've applied street trees for the remaining 2,750 square feet. We can use an area weighting approach to determine what an area weighted DHSC relates to. And so in this case, now we're down to 0.2 inches. So at a site scale for this drainage management area, we have an effective hydrologic source control depth of 0.2 inches. So now we're going to see how this influences our simple design capture volume sizing method. So this method involves first looking up the design capture storm depth, then claiming the adjustment to the hydrologic source controls that someone has calculated already based on what's been applied, computing what portion of the DCV remains, designing the BMP to essentially capture that DCV, so designing BMP for that physical storage volume that we've calculated, and then demonstrating that it drains in 48 hours or less. So we'll just take we'll follow through on this example. We have an 85th percentile storm depth of 0.85. We have a 1.25 acre site, 80% impervious with an effective retention depth of 0.2 inches for the whole site, and a design infiltration rate of 0.5 inches per hour. So the first step we're going to do is subtract hydrologic source control depth from the design storm depth. So now we've gone from 0.85 inches down to 0.65 inches on the basis of using those hydrologic source controls, documenting them, and explaining them in the WQMP. So now we're going to compute the remaining DCV. And so here what we see is that when we apply 0.65 instead of 0.85 in this calculation, we've gone from a volume of 2,200 down from a volume of almost 2,900. So if we're going to value this on the range of $10 per cubic foot, maybe $20 per cubic foot, the designer has just saved himself on the order of $12,000, by just claiming the hydrologic source controls and filling out a couple of fact sheets and and ensuring that those downspout disconnects actually get incorporated into the plans. So now we move along with our sizing. Now we have a volume, but now we have to decide how are we going to provide that volume in our BMP. So this is a simple example where we have vertical walls. We can assume everything is just a vertical profile, and we can calculate, you select 9 inches of ponding, 24 inches of soil with an available capacity of 0.15 inches per inch in the soil. And so you end up with a total storage depth of 12.6 inches of water equivalent. So now what we're going to do is we're going to check and make sure that that profile actually drains in the requisite amount of time. So we can take that 12.6 inches, divide it by K design, 12.6 inches over 0.5 inches per hour, and we can see that in this case we're draining this whole entire storage volume in 25 hours. So that's less than 48, that's good. The system will capture even more because it'll empty even faster than the requirement. And so, if we now put this thing into a footprint, we can take that 2,200 cubic feet of storage, we can divide by that 12.6 inches of water equivalent, or equal to 1.05 feet, and we can determine that this site is going to need 2,100 cubic feet worth of, or square feet worth of BMP footprint in order to capture that design capture volume. And so that's going to translate, in this case, to about 4% of this drainage management area. And this is an example of the completed worksheet that shows each one of these calculations line by line, showing how they subtracted their hydrologic source controls, how they calculated their design volume, how they determined what their design infiltration rate was, how they determined that the drawdown time was less than 48 hours, and then finally how they calculated their square footage for the BMP that's required. So the capture efficiency sizing method, I guess the first question is, why would someone use this? Because that other one was so easy and it was simple and really clear. I guess the main reasons is when you have a situation where draining in lower or higher than 48 hours is natural for the site. And you want to account for the benefits on sizing that you could get from draining in more or less than 48 hours. In some cases, you might have a hydromod BMP that by the nature of how it's supposed to be discharged drains in more than 48 hours. In that case, you may need to use the charts to be able to show that this hydromod BMP, even though it drains in more than 48 hours, it's adequately upsized in order to still capture 80%. So the general process for capture efficiency sizing starts with the same, looking up the design storm depth, computing the effective hydrologic source controls. You select the system geometry, you compute the drawdown time associated with the system geometry. Now what happens is, now that you know the drawdown time of the system, we can pick the actual right line on the chart to correspond to that drawdown time for the nomographs, and you can compute what actual fraction of the design capture storm volume is necessary. So we'll start with the same example. In this case, we have all of these knowns. Everything is the exact same as what I described previously, the same profile, the same hydrologic source control credit, the same design capture volume, same drainage area. So the first thing we're going to do is go to this table and say, well, I have 0.2 of an inch of hydrologic source control. What does that correspond to in terms of a capture efficiency? And that corresponds to 37% capture efficiency. So we can start there. Now we know we have a 25-hour drawdown, so we'll go to the 24-hour curve. That's almost exactly the same as 25. And we'll say, okay, so what total fraction of the design capture volume do I need to achieve in order to get to 80% capture? So we'll start with 80%, draw over until I hit my 24-hour line, and draw down and say, well, I need about 79% of my design capture volume to get to 80% capture. So even if I didn't have hydrologic source controls, I've already saved about 20% on sizing by accounting for drawdown time. But now I can claim the 37% capture efficiency that I've already achieved. So I'm drawing over to the same line, I'm drawing down, and I'm saying that corresponds to a fraction of the design capture volume of about 0.19. So now the difference between these two is the amount that I need to make up in my LID BMP in order to get up to an 80% capture, up to an 80% capture level. And so now what I have is I need to provide about 6/10 of the design capture volume in order to achieve full compliance here. So now we'll multiply 0.6 times 0.85 to adjust that design capture volume down. We'll be at 0.51 and compute the runoff from that. So now we're at 1,736 cubic feet. So we've essentially taken our footprint from 2,100 square feet down to 1,650 square feet by accounting for the fact that this system drains in a faster amount of time. And this is another worksheet that associated with this method that someone can use to document that they've gone through this method accordingly. And you'll also see a set of nomographs that they can use to mark up. So what you should expect to see in your submittal if someone does go this route is this worksheet filled out as well as a nomograph with hand markings or digital markings on it that shows you the pathway that they took to determine that they've made it to 80% capture. So I think I'm going to, we'll get through this slide and then I'm going to hand it off. So now let's talk about biofiltration sizing. So we've subtracted our hydrologic source controls. Now what we've done is we've subtracted any volume that's retained already, either upstream of the BMP. I mean, we still can allow people to use two-part systems. They could use an infiltration trench and then down to a biofiltration BMP. But more often we're going to see that stacked configuration where we have the volume below the underdrains and the volume above the underdrains. So in this case, we would subtract the volume that's below the underdrains or upstream. And now we're going to compute the remaining design capture volume that needs to be biofiltered. We can do either biofiltration, we can size our biofiltration element to be equal to the remaining design capture volume, and ensure that it drains in no greater than 48 hours. So essentially just following along with the same simple design capture method approach. Or what we can do is we can continue on with the capture efficiency method, and we can calculate what percent capture has already been provided upstream as a part of hydrologic source controls and our retention system. And now we can build up, essentially, using the graphical methods in those nomographs, we can build up to figure out what capture efficiency is or what additional biofiltration storage is necessary to get us up to a cumulative 80% capture. And at the same time, we'll have to check back and forth that that's not less than 75% of this remaining design capture volume, so that we keep the permit happy. I'm going to stop now, make sure we have plenty of time for the HMP and those illustrations. But this is one part of the TGD where we have some really good examples of working through this, and should provide a good reference for you in Appendix 3.